Hi everyone, Assalamualaikum. In this video, we are going to discuss example for C for radioactive decay under applications of first order ODE. Carbon-14 has a half-life of 5,715 years. A fossil has lost 75% of its original amount of C14. How old is the fossil? How much C14 remains after 50,000 years? Right? To solve this problem, first we need to extract all the information and write in terms of T for time and P for population. Right? Now we check one by one. Okay? From the word half-life of 5,715 years, we can write T equals to 5,715 years. P equals to half P naught. Okay, P naught means original P. Okay, so this is from the word half-life. Alright, and lost 75% of its original amount. Okay, so we can write P equals to 0.25 P naught. Okay, why we write this? Because lost 75% of its original amount. So means 25% remains. 25% means 25 over 100. And 25 over 100 equals to 0.25. Okay. P naught here because of its original amount. Right? Right. And then how old is the fossil? Okay. How old means in terms of time. Okay, so T equals to question mark years. Okay, and then from the word how old, we can write this. Okay, T equals to question mark and then years. Okay, alright, and then the next question, how much C14 remains? So we can write P equals to question mark. This is amount remains. And then after 50,000 years, so we can write T equals to 50,000 years. Okay, this is the next question. Okay, this is question 1 and this is question 2. Right? Alright, from here, the initial condition, the initial P is not given. Okay, so we need to write T equals to 0, P equals to P naught. Okay, this is the initial population or the initial P. In this case, the initial mass of this fossil. Alright? Right, so to solve this problem, we need to start from D population over D time equals to Kp. Okay? Then, separating variables T and P. Okay? We move dt over dt here to right hand side, so we get times dt. And then at the same time, we move P to left hand side. So we get times 1 over P. Okay. So now we have 1 over P dP equals to K dt. Okay. After that, integrating both sides. From this equation, we just put integration sign for both sides. Okay. And then we integrate left hand side and right hand side. When we integrate 1 over P dP, the answer equals to ln P plus C. And when we integrate K dt, the answer equals to K constant and then T plus C. We just write plus C on one side only. Alright? For left hand side here, we refer this formula. When we integrate 1 over x dx, the answer equals to ln x plus C. So, if we integrate 1 over P dP, the answer should be equals to ln P. Alright? And then to integrate constant K dt, we can refer this formula. Let's say if we want to integrate constant 2 dx, the answer equals to 2x because now we integrate with respect to x. And then plus C at the back. Now we want to integrate constant K dt. So the answer equals to KT plus C. Alright? Alright, after that, we want to write P as a subject. Okay, so to write P as a subject, we need to move ln to right hand side. So when we move ln to right hand side, so we get this. Okay, P equals to E. When we move ln to right hand side, we get index base E and then to the power of KT plus C. Alright, and from here, we can use properties of indices. We can separate to e to the power of k times e to the power of c from this formula. A to the power of m times a to the power of n equals to a to the power of m plus n. So now we have e to the power of kt times e to the power of c equals to e to the power of kt plus c. Alright? We reverse this formula. Alright? And then from e to the power of c. Okay, e means Euler number, which is equals to 2.718 something, which is constant. Constant time constant will equals to constant. So we can write e to the power of c equals to c. Okay, so now we have p equals to ce to the power of kt. Okay, after that we name as equation 1. Right? From the previous slide, we extract all the information in terms of T for time and P for population, and then we write P equals to C e to the power of KT and we name as equation 1. Okay. After that, we can substitute this information to find C, and we substitute this information to find K. Right? To find C, substitute T equals to 0, P equals to P naught into equation 1. Okay? From equation 1, P equals to C e to the power of KT. So now we replace P equals to P naught and we replace T equals to 0. 0 times K equals to 0. E to the power of 0 equals to 1. C times 1 equals to C. So we get C equals to P naught. Alright. After that, we substitute C equals to P naught into C in equation 1 here. So we get P equals to P naught e to the power of KT. Yeah. We substitute C equals to P naught into C in equation 1 here. So we get this. Right? After that, we name as equation 2. Right? Right, then we substitute this information to find K. Okay? To find K, substitute T equals to 5,715 years and P equals to half P naught into the latest equation into equation 2. Okay? So from equation 2 here, we replace T equals to 5,715 years and we replace P equals to half P naught. Okay? After that, we can simplify P naught for both sides. Okay, then we have e to the power of 5,715k equals to half. Alright? We get back half because from the word half life here. Alright? Right, after that, now we want to find k. So we need to move e to right hand side. So after we move e to right hand side, so we get left hand side 5,715k equals to ln. Okay, after we move e to right hand side, we get ln and then half. Right? Then we can find the value of k equals to ln half over 5715. Or we can use calculator and it's equals to negative 0.00012 up to 5 decimal places. Okay. From here, we have k in negative value because the radioactive is decay. Okay. Right. So from here, we substitute the value of K into equation 2. Okay, so after we substitute, we get this. Okay, we can substitute either this value or this value. Okay, but if we use this value, the answer is more accurate. Okay, compared to this. Alright, so after we substitute, K equals to ln 0.5 over 5715 into K in equation 2 here. So we get this. Okay. P equals to P naught e to the power of ln 0.5 over 5715t. And then we can name as equation 3. Alright. Equation 1, 2, and 3 are the same equation. Equation 1, we still have C and K. Equation 2, we substitute the value of C. And equation 3, we substitute the value of C and K. Alright? From the previous slide, we get P equals to P naught e to the power of ln 0.5 over 5715t, and we name as equation 3. This is an expression for the population or mass at any time t. Okay, and then from the question here, a fossil has lost 75% of its original amount of C14, and then how old is the fossil? So we can write this, right? Then we can substitute this information into equation 3 here. Okay. So this is how old is the fossil, right? So substitute P equals to 0.25 P naught into equation 3. Okay. From equation 3 here, we replace P equals to 0.25 P naught. Okay. After that, we can simplify P naught on both sides here. So we can write e to the power of ln 0.5 over 5715t equals to 0.25. No more P naught because we simplify P naught on both sides. Alright. Now we want to find t. Okay. So we need to write t as a subject. Okay. We need to move e to right hand side. Okay, so from E here, when we move to right hand side, we get left hand side ln 0.5 over 5715t equals to ln. When we move E to right hand side, we get ln here and then 0.25. Alright. Then t equals to ln 0.25. We move this fraction to right hand side, so we get times and then we multiply by this fraction, but we need to exchange numerator and denominator. So we get times 5715 over ln 0.5. And then using calculator, t equals to 11,430. We need to put a suitable unit. From here, we have years here, so we write years. Okay. Then we can write the fossil is 11,430 years old. Right? So this is the answer for question 1. Okay, for this question. Right? From the previous slide, we get an expression for the population at any time t is given by P equals to P naught e to the power of ln 0.5 t over 5715, and we name as equation 3. Okay? Or we can write P equals to P naught e to the power of t ln 0.5 over 5715. We move t to the front here. Okay, to avoid error, we better put t in front here because t cannot multiply by 0.5. Okay, because 0.5 is inside ln, right? So to avoid error, we better put t in front here when we calculate. Alright, then we can name as equation 3. Okay, because actually these equations are the same. Alright. Alright, from the previous slide, we done solve number Roman 1. Okay. So now we continue with number Roman 2. Okay. We substitute this information into equation 3. Right? Number 2, substitute t equals to 50,000 years into equation 3. Right? From equation 3, we have P equals to P naught e to the power of t ln 0.5 over 5715. Now we replace t by 50,000. Alright? Then using calculator, e to the power of 50,000 ln 0.5 over 5715, we can use this step. Right? Bracket and then shift ln for e to the power of any value. Okay. And then open bracket and then 50,000 times ln in bracket 0.5 and then we close bracket 3 times because we open bracket 3 times. So we need to pass with close bracket with 3 times. Alright. And then over 5715. Alright. Then from here, after we use calculator, so we get 0.0023 and then we still have P naught here, right? Alright, since the original amount was not given, okay, so we need to write the answer in percentage form, okay? So from here, we can write P equals to 0.0023 times 100%. P naught, okay? Times 100% here means 100 over 100, which is equals to 1. So it doesn't change the original value, okay? But we need to read in terms of percentage form, right? So after that, we have P equals to 0.23% P naught, right? Then we can write after 50,000 years, C14 remains 0.23% from the original amount. Right? This is the final answer. Okay? We write in the form of percentage because the original P was not given. Right? Up to this point, we done discuss 3 examples under number 2, radioactive decay for application of first order ODE. Coming up next, we continue with number 3, which is Newton's law of cooling and the applications of separable differential equations. If you like this video, you can subscribe. Thank you for watching. Stay tuned. Bye. Assalamualaikum.